Hello, everybody. Let's continue with the problems from where we had left in the last session. In this problem, also, we are asked to find out the DTFT of the signal, but how this problem is different. In the problems that we've seen so far, the expression for x of n was given, but here the sketch of x of n is given, which is quite simple. It is a discrete signal, okay, which is 1 at n equal to -3, -2 and 2, and -1 at n equal to 3. So this is what is the signal, and we have to find the DTFT of the signal. Let's see how the solution looks like. As usual, the DTFT equation is considered. X of n is the discrete time domain signal that is given, and the frequency domain signal of this x of n is x of e power j omega, which is also called the spectrum of x of n, which gives the frequency information of the given signal. Now, there are only 4 non-zero samples. Okay, there are only 4 non-zero samples, as can be seen here. Okay, so let's expand this and just try keep the samples which are present in the given signal. Here, x of -3, this sample is there. Then x of -2 is there. X of 2 is there. Then x of 3 is there. So as was the case in Z transform, all left-sided samples are associated with the positive exponentials. There it was positive powers of Z. Here it is positive exponentials. Similarly, all right-sided samples are associated with negative exponentials. This is a generalized equation, but the terms are written, the samples are written only for the given instance of time here where samples exist. Fine. So let's just bring in the values of these samples in this equation, and it looks like this. Fine. So we have exponent. We have samples equal to 1 at these n's and -1 at n equal to 3. This is 1 at n equal to 2, 1 at n equal to -2, 1 at n equal to -3. Okay, and this is -1 at n equal to 3. That is what is the signal given. Now these exponentials can easily be expressed in terms of the sinusoidals. Okay, how? E power j3 omega is there, and here you have e minus e power minus j3 omega. So these two will constitute sine signal, okay, and these two will constitute the cos signal as shown here. Okay, in the denominator of sine you will have 2j, so it is 2j times 3 omega, and this is 2 times, sorry, these two, okay, and it is 2 times cos 2 omega, because there is plus between these two, and since there is a minus between these two, so it becomes sinusoidal signal. Since there is 2j in the denominator, that is compensated by taking this 2j here in the numerator along with the sinusoid. Fine, so this is quite a simple one. The magnitude and phase spectra, they were asked, as you can see here, the expressions, find the expressions for magnitude and phase spectra is asked. Okay, so we do not have to sketch the magnitude and phase spectra. So let's just write the expressions for the magnitude and phase spectra. Okay, so which is this? This is the magnitude. This is a plus jb form. This is a complex number. If you have to treat this as a number, this is a signal anyways, but it's a complex signal. Okay, so if you have to obtain the magnitude of this 2 is common, just keep it out. Okay, this is cos 2 omega plus j sine 3 omega. So if this is a and this is b, the magnitude is square root of a square plus b square. So yeah, square root of cos square plus sine square. Fine. Now what is phase? This is the symbol they use to denote the phase of the signal. Okay, but there are different notations also, but let's use this notation, and as you all know, it's tan inverse of b by a. Okay, now is it minus tan inverse of b by a? I am doubtful. Yeah, see that if it is minus or it's just tan inverse of b by a. Okay, so if it's minus, we need to bring that here. Fine. So this is how we obtain the expressions for magnitude and phase spectra. Okay, so let's move on to the next problem. That is this. Again, a discrete signal is given, which is non-periodic in nature. Okay, since it is non-periodic, we are going for obtaining the DTFT. If it were periodic, we would have gone for DTFS. Understand that, right? Okay. Now again, the task here is to find the range of this signal. What is the range of this signal? So what is this signal? Just this. Let's come to the combination of this later on. Just tell me what is u of n plus 3. U of n plus 3 is shifting u of n to the left by 3 units. To the left by 3 units means now it starts at minus 3 and goes till infinity. This u of n minus, this is shifting u of n to the right by 2 units. So it is, its range is from 2 to infinity. So combined range, if these two, if you subtract this signal from this signal, okay, you will get a rectangular pulse of width, what, of range. Let's talk about the range, minus 3 to plus 1, minus 3 to plus 1. Okay, so that is what we need to understand here. So this is actually defining the range of this signal. Okay, so let's substitute the given signal here. In the next step, this has to be 1, and this is 1 over what range needs to be told. So it is minus 3 to 1. Okay, most of the students misunderstand. If it is continuous in time, if it is u of t plus 3 minus u of t minus 2, then it is from minus 3 to 2. But since this is discrete in time, it is from minus 3 to 1. That's why this is taken from minus 3 to 1. So this signal is 1 from minus 3 to 1. Okay, now we can combine these two terms. Okay, taking n as the power, common power of both the terms. That is done here. Now this summation is not in the standard form. What are the standard summations that we've seen? The summation should either go from 0 to infinity or 0 to some finite number or some finite number to infinity. There are three such standard summations we have seen. Now this is a finite summation. Okay, so it is starting at minus 3 and it's going till 1, and this is not a standard form. We need to bring this to the standard form. What's the way we can bring it to the standard form? We can take this minus 3 onto the left, so it would become n plus 3. Okay, that is the way we start doing, because when we do n plus 3 here, okay, so what happens? It would look like n plus 3 equal to 0. In other words, when you take this minus 3 to the left hand side, it becomes n plus 3, and on the right hand side it becomes 0. That means it is n plus 3 plus 3. It's as good as adding plus 3 to this equation here. So it's n plus 3 equal to minus 3 plus 3. What happens here? Here if it is infinity, we could have neglected this part, but this is 1. So it would be 1 plus 3. So this is something one needs to take care of. Fine. I repeat, when I'm shifting the lower limit, the upper limit would also shift. If it is infinity, the shift is not a matter. Anyways, this is infinite. But if this is a finite number, the shift that we have here in the lower limit should also reflect on the upper limit. That's why I'm saying it's as good as adding plus 3 to this. So when you do adding plus 3 here, so you have to be adding plus 3 here also. Is that the way they do it? Okay. So here it is 0. So this should have been, yeah, let's see. N plus 3 is equal to 0. Okay, this should have been 1 plus 2. Yeah, see here. This is n plus 3 equal to 0. This has to be also plus 3. So it's 1 plus 3. See it has become 4 here. Everybody understand that point? Why this became 4? Okay. So here it is adding plus 3. So it should become plus 3 here. So if you are noting it down, please note down that it is supposed to be 1 plus 3. This is n plus 3 plus n plus 3 equal to minus 3 plus 3. So it is 1 plus 3. Okay. So take this as 1 plus 3 and that is how it becomes 4 here. That's missing here. Plus 3 is missing. Okay. That's why it becomes 0 to 4. Now this is some standard form, but we need to deal with this. What did we do? This n plus 3 is taken as L. So L is going from 0 to 4, but there is a n here. So when we are operating with L, this cannot be n. So if this is L, what is n? N is L minus 3. So n is substituted as L minus 3. So keep the function of L inside the summation and keep the signal which is not the function of t outside. Okay, function of L rather. So this is how it looks like. Okay, half e power j omega to the power minus 3 is kept out of the summation and the function of L is kept inside. So this is the standard form. Which standard form are we talking about? Here, this is the standard form. 0 to some finite number. 0 to some finite number. Here, 0 to some finite number. Okay, so this is another standard summation that we can see. Fine. So it looks like this. If alpha is not equal to 1, it is this 1 minus alpha to the power n plus 1. Yeah, this would become n plus 1. If it is 0 to n, here in the numerator it is 1 minus alpha to the power upper limit plus 1 divided by 1 minus alpha. So when would this be true? This is true when alpha is not equal to 1. Understand that? Okay, and when alpha is 1, it is 1 to the power n. 1 to the power n is anyways 1. So how many times you are going to add this 1 if alpha is 1, I'm saying. If alpha is 1, how many times you're going to add that? 1. See here? 0 to n times. 0 to n times 0th 1 is there. First time, second time, third time. Okay, it starts at 0. If it's from 1 to n, it is n. If it is 0 to n, it is n plus 1. So if alpha is 1, it is n plus 1. If alpha is not equal to 1, then this is this. In our case, this is not 1. Okay, so that's why our spectrum can be written like this. Understand that? Okay, see here. This is 4, right? So it becomes 4 plus 1. That's why this 5 is there. 1 minus alpha to the power. This is alpha to the power 5 divided by 1 minus this the term. Okay, this is something that we had kept out as constant, which was not the function of L. Is kept out, and this is how it looks. Fine. Hope you have understood. So this problem is important from this point of view. Okay, there should be a plus 3 since you're doing plus 3. That's why this one has become 4. Okay, so remember that. Now let's move on to the problems where we find out the DTFT using the properties of DTFT. We have seen the properties of DTFT. So let's see some simple problems, okay, using the properties of DTFT. This problem can even be solved using the definition of DTFT. Definition of DTFT means the equation for x e power j omega. We can find the DTFT, but since they've asked us to use the appropriate properties, so we need to use the properties. And when we are asked to use the properties to find out the DTFT, so what is one thing that we need to be careful about? Here you have shifted version of u of n, okay, but this n is not shifted. So this is the problem here. Okay, so somehow you need to try get this also as n minus 2. Fine, so this is not new to you, this has already been discussed. Okay, we've solved so many problems on this, so the same rule applies here also. Okay, when you have this as n minus 2, you're not supposed to have this as n. Somehow we have to make this n minus 2 keeping the given equation without change. Okay, so given is this equation, it can also be written as, okay, half to the power, what is supposed to be there, half to the power minus 2, right? So if half to the power minus 2 comes along with this, okay, to compensate that we need to have half power 2. So it's as good as multiplying this equation, or as good as having the right side, okay, being multiplied 1. So it's half square into half power minus 2. So that is what is the term we have got there. Okay, so minus 2 comes with this term, okay, and the square term is here, okay, which would be a scalar. Fine, but scalar can be taken care of at the end. Now we need to take care about this. Okay, and we all know when we are asked to find out the DTFT using the properties, we have to identify the basic signal. Which is the basic signal? This is shifted signal. So without shift, which is the signal? It is half power n u of n. So do we know the equation for that? Yes. So we used to write it, if it is z transform, we used to write z by z minus half, right? Z by z minus half. So in other words, it can even be looked at as 1 minus half z inverse. 1 minus half z inverse. So they are dealing with in terms of inverses. That's why it looks different. Understand that? So this is as good as z inverse. So if you want to make this positive to become e power j omega divided by e power j omega minus half. So we can do that way also. Fine, but since they are trying to have the inverse or the negative exponentials only, let's move on with it. Let's get used to both the steps. So we have tried having the positive powers of z when we did z transforms. Here the problems that we are seeing have negative exponentials. That's the difference. Otherwise it's almost like your z transforms only, wherein z is replaced by e power j omega. Fine. Now half power n u of n is taken. Now there is n minus 2. This is not the given signal. We need this to be n minus 2 and this also to be n minus 2. That means which operation we are performing? We are performing which operation? The shift operation, the time shift operation. Okay. So if there is a time shift, we have to be using the time shift property, since we are asked to use the properties. See, using the time shift property, this is true. If you have x of n, the DTFT of that looks like x of e power j omega. If you have shifted x of n, that shift is reflected in the frequency domain with the use of this exponential. Since there is minus n naught, okay, you have e power j omega to the power minus n naught. So we used to have z to the power minus n naught. What is the z transform of this? It is z to the power minus n naught into x of z. Very similar, very similar to that. Okay, except that the z is replaced by e power j omega. This is the same property. So if you have understood the z transforms, if you have worked out with the z transforms, okay, in depth, so if you have fair understanding of z transform, this should not be difficult for you. Fine. So since there is a shift, okay, how is this going to look like? We already have the equation, the DTFT of half power and u of n. So let's keep it as it is. Okay. So along with that, we have to bring this exponential. So this is the DTFT of this term is the DTFT of half power n u of n. Since we have half power n minus 2 and u of n minus 2, this exponential comes. Since there is minus 2, okay, it is e power j omega to the power minus 2. It's like that. Now this is not the only signal, there is a scalar along with it. Okay, so using the linearity property, if there is a scalar, okay, the DTFT, how it looks like, just bring the scalar there. It's 1 by 4 times. This scalar is just carried forward. Fine, along with the DTFT term. Fine, that's why the DTFT of the given signal looks like the right hand side here. Understand? So this is quite a simple problem. In the syllabus, he has told the simple problems, the basic problems. Okay, so that's why I'm trying to keep it as simple as possible. When I've not taken the complex problems which are there in the textbook. Fine, so let's limit ourselves to the basic ones. So next is this. Okay, again using the appropriate properties, you have to find the DTFT of this signal. So have you seen the sinusoidal signal? So if you have seen that, it would work, otherwise no. Fine. Now here, see here, you have n minus 1, but this is one standard signal. So here we also need n minus 1. So how to take care of that? This sinusoidal is written as the complex exponential here. Okay, since we wanted minus 1 here, okay, so half power minus 1 and sorry, 1 by 4 to the power minus 1 and 1 by 4 to the power 1 is taken. This is the compensation of 1 by 4 to the power minus 1. Fine. Now keep these two out and multiply these exponentials along with the signal. Okay, so let's not bother. We are having a big equation. It boils down to simple thing. Okay, if you understand the properties, let's see that property. It's quite a simple one. Fine. So let's bring this 1 by 4 and 1 by 2j is right there. So that is kept out as 1 by 8j. Okay, and these exponential. So this is one exponential we have which needs to be associated with the signal here. This is another exponential which needs to be associated with this signal. So this signal is associated with some exponential. Okay, so when would there be an exponential in time domain is the question. When would there be an exponential in time domain is the question. So that is what is the solution of this problem. Okay, so if you know the answer for that question, you know the solution for this. Let's learn what is that. Fine. Now let's try catch hold of one of these terms. Fine. Let's just deal with this. So what is the standard signal? It is 1 by 4 to the power n u of n. So as we have seen in the last problem, it was half. In this problem, it is 1 by 4. That's it. Okay. So it would be 1 by 1 minus 1 by 4 times e power minus j omega. Okay. Now there is a shift. Okay. Let's make this as 1 by 4 to the power n minus 1 and u of n minus 1. So this is time shift property as we have seen in the last problem. Okay. Now, since there is a shift, there is an exponential attached in frequency domain. So if there is a shift in time, the exponential is attached in frequency domain. If there is a shift in the frequency, what? Yeah, since this is there, so they have combined these two and they have arrived at a simplified form of this. Since there is an exponential in the time domain, okay, since there is an exponential in time domain where in the given signal, in the given signal sinusoidal was there, that sinusoidal is expressed in terms of the complex exponentials, and these complex exponentials are now coming along with this. Okay, so that is what it means. Since there is an exponential in the time domain, we use the frequency shift property. See, if there is shift in the frequency, what is the frequency? If there has to be a shift in the frequency, it is frequency domain. Okay, the shift is in the frequency domain. So in the frequency domain, see here in the frequency domain, you have omega as the frequency, and that frequency is being shifted by minus beta. So this has to be reflected in time domain by associating an exponential here. If it is a time shift, there is an exponential in frequency domain. If this is frequency shift, then there is an exponential in time domain. But yes, you need to be careful. Where you need to be careful here, if you have -1 as the shift, that -1 is shown as -1 here on the right hand side. See here, this, not this. E power j omega to the power -1. So if it is -1 in time domain, -1 only in frequency domain. But if it is minus beta in the frequency domain, then it is plus beta in the time domain. If it is plus beta in the frequency domain, it would be minus beta in the time domain. Okay, simple stuff. So that is what is true here. So there is u of n minus 1 and there is an exponential, right? So for if there is an exponential here in time domain, we know that there has to be a shift in frequency domain. So what is that shift? It is plus pi by 4 is there. Okay, so it has to be taken as pi by 4, omega minus pi by 4. Fine. So similarly, using linearity, you can bring this 1 by 8j. So 1 by 8j would get carried in the frequency domain also. So similarly, we have another term there. This is for one term. Okay, there is another term like that. So what I mean is this. Yeah, we did it for this term. Very similarly, you have the other term. What is the only difference? You have minus j here. You have plus j here. You have minus j here. Except that everything is same. So what is the frequency shift difference is what we need to understand. Okay, so this is for the first term. This is for the second term. See here, if you have plus pi by 4, so you have minus pi by 4 in frequency. You have minus pi by 4 here, so you'll have plus pi by 4 in the frequency. So these two terms you obtained. Okay, so therefore, for the given x of n, okay, the DTFT looks like this. 1 by 8j you just keep as it is. The DTFT of this is obtained here, and the DT of the second term is obtained here. In both the terms we have 1 by 8j as common. Okay, and just write the remaining terms here. When if it's a big equation, let's not go for simplifying it further and keep that in a sinusoidal form. Okay, so it becomes very time consuming stuff. So let's stop. If you can go one step ahead and express that in terms of sinusoidals, it's good. But see, if time is permitting you, you do that, or else you can stop here, right? Anyways, they have not asked us to express the DTFT in terms of sinusoidal. They're not particular about it. Yes, the given x of n is in terms of sinusoidal. Okay, but since it's a time consuming process, because it's just simplifying the things and expressing it in terms of the other terms. Okay, if the time permits, you go for that. Otherwise, we can keep here. Okay, we can stop here rather. Fine. So let's move on with the signal. Okay, wherein they're asking us to find the DTFT of the signal. Okay, using the what? No, this problem is not using the properties. Okay, so let's see this again in the next session. Let's stop this session now.